Welcome to a lesson on exponential functions with base e, sometimes referred to as the natural exponential function. So an exponential function with base e is in the form f of x equals a times e raised to the power of kx, where a can't equal 0 because if it did, we'd have a constant function. K is equal to the continuous growth rate, and the base e is an irrational constant, which is approximately 2.718, often referred to as Euler's number. A is also equal to the initial value or starting amount, which is the function value when x equals 0. Notice when x is 0, we'd have a times e raised to the power of 0, which would be equal to a times 1, which equals a. Which also means the vertical intercept would be the ordered pair 0, comma a. And if k is positive, then the function represents exponential growth with a continuous growth rate of k. And if k is negative or less than 0, the function represents exponential decay with a continuous decay rate of the absolute value of k. So it's important to recognize here that when we have base e, the growth rate and decay rate are continuous rates. This was not the case when we had exponential functions in the form f of x equals a times b raised to the power of x. Now let's look at this graphically. Here we have the graph of f of x equals 5 times e raised to the power of 0.14x. Notice how k is positive, k equals 0.14. This tells us our function is going to be increasing, and we have exponential growth, as we see here. This also tells us the continuous growth rate is 14%. And also notice that a is equal to 5, and the vertical intercept is 5. Looking at the table of values, again we can see that as x increases, the function values increase, but now they're increasing at a continuous growth rate of 14%. Next we have the graph of f of x equals 18 times e raised to the power of negative 0.35x. So notice how here k is negative 0.35. This tells us we have exponential decay, and therefore the function is decreasing, and it's decreasing at a continuous rate of 35%. Also notice here that a is equal to 18. 18 is also the vertical intercept. And looking at the table of values, as x increases, the function values are now decreasing at a continuous decay rate of 35%. Let's look at an application problem. E-Energy, an all-natural energy drink company, had revenue of $550,000 in 2012. The revenue is increasing exponentially at a continuous rate of 22.4% per year. Write the exponential function to model the revenue. Let t be the number of years since 2012, and r of t be the revenue in thousands of dollars. Predict the revenue in the year 2014 to the nearest dollar, then predict when the revenue will double. Notice here, because we have a continuous growth rate, we can model the revenue using an exponential function with base e. So the revenue function is going to be in the form of r of t equals a times e raised to the power of kt, where again a is the initial or starting amount, k is going to be the continuous growth rate, and t is going to be, in this case, the number of years since 2012. So starting with a, we need to be a little bit careful because r of t is in thousands of dollars. So a is not going to be 550,000. A is going to be just 550, again because the function value is in thousands of dollars. Next, the continuous growth rate is 22.4%, and therefore k is equal to 22.4% as a decimal would be 0.224. K always must be expressed as a decimal. And this is all the information we need in order to write our revenue function. We would have r of t equals 550 times e raised to the power of 0.224 times t. And now we'll use this function to answer the next two questions. So for part B, we're asked to predict the revenue in the year 2014 to the nearest dollar. Well, 2014 is 2 years after 2012, and therefore we want to evaluate the function r of t when t equals 2. But If we ever have a hard time determining the value of t to use, we can always determine t by taking the desired year, in this case 2014, and subtracting the base year, in this case 2012, which will give us t equals 2. So we want to find the function value r of 2, which would be equal to 550 times e raised to the power of 0.224 times 2. We need to be careful here though, because remember r of t is going to be in thousands of dollars. So now we'll go to the calculator and we'll enter 550. Now for e, if we press second natural log, that brings up e raised to the power of, and I'm going to go ahead and put the exponent in parentheses, where the exponent is going to be 0.224 times 2. Close parenthesis and enter. Because this is in thousands of dollars, we'll round this to 3 decimal places, which should be to the nearest dollar. So we'd have 860.848. Again, this represents thousands of dollars. So if we want the units to be dollars, we'd have to take 860.848 and multiply by 1,000, which is the same as moving the decimal point to the right 3 times, or 3 places, which should be 860,848. Which means in 2014, the revenue is predicted to be $860,848. Now let's take a look at part C. Now for part C, we're asked to predict when the revenue will double. Well, remember the starting revenue is 550,000, which in our function is equal to 550, and therefore the revenue is going to be doubled when the function value is twice 550, which would be 1,100. To determine when the revenue is going to double, we're going to set r of t equal to 1,100 and solve for t. So we'd have the equation 1,100 equals 550 times e raised to the power of 0.224 t. And now we'll solve this 2 ways. If you haven't learned about logarithms yet, we could always solve this graphically by setting the right side of the equation equal to y1 in the graphing calculator, setting the left side equal to y2, graphing the 2 functions, and determining the point of intersection. The point of intersection will give us the value of t that would satisfy this equation, and therefore help us determine when the revenue will double. I've already done some of this to save some time. So if we press y equals, notice how I've already entered the right side in y1, though I use the variable x instead of t, and I've entered 1,100 in y2. Now before we graph this though, we do need to adjust the window. So if we press the window key, right now the x-axis goes from -5 to 30, which is probably going to be okay. Now for the y-axis, we know we have to have a y maximum that's at least 1,100. So let's go down to the y-axis, and let's change this to go from, let's say, -200 to, let's say, 1,800. And we'll have a y scale of 200s. Of course, if this doesn't work, we can always come back and change it. Now let's press graph. So there's the exponential function, and here's our constant function, y equals 1,100. We can answer this question by determining this point of intersection here. So we'll press second trace for the calculation menu, option 5 for intersection. Now we can just press enter 3 times. So enter, 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 and notice how we have approximately 3.09 for the value of x, which is really the value of t. So graphically, we know the solution is t is approximately 3.09, which means the revenue is going to double approximately 3.09 years after 2012. Let's also solve this algebraically before we interpret what year this would be. So to solve this algebraically, we'll have to use logarithms. For the first step, we want to isolate the exponential part of the equation. That means dividing both sides by 550. Simplifying, we have 2 equals e raised to the power of 0.224t. And now we're going to use logarithms to solve for t. And because we'll be using the calculator, we can use common log or natural log. But because we have base e, it'll be more convenient to use natural log. So we'll take the natural log of both sides of the equation. So now we have natural log 2 equals, on the right side, we're going to apply the power property of logarithms, which means we can take this exponent and write this as a product times the natural log. So we'd have 0.224t times natural log e, but natural log e is equal to 1, so that simplifies to 1, and therefore to solve for t here, we just divide both sides by the coefficient of 0.224. Simplifying on the right side, we just have t, and now we'll approximate the quotient on the left. Notice how natural log 2 divided by this value here, which is just k, gives us the doubling time. So back to the calculator, back to the home screen, so second mode for the home screen, which are natural log 2, close parenthesis, divided by 0.224, enter, which of course gives us the same value that we found graphically, of approximately 3.09. Now that we know the revenue is going to double approximately 3.09 years after 2012, let's interpret what year this would be. If we consider the year when t equals 3, that would be the year 2012 plus 3, which equals 2015. But it's important to recognize that when t equals 3 and we get the year 2015, this is the end of the year of 2015. So any value of t greater than 3 and less than 4 would actually be in the following year of 2016. So to answer this question, we would say the revenue is predicted to double in the year 2016. This can sometimes be tricky to interpret because some textbooks may just round the value of t to 3 and say it's actually going to be in the year 2015. But again, it's important to recognize that any value of t represents the end of that year, and therefore if it's a little bit larger than a given value of t, it would be in the following year. Of course, it'd be toward the beginning of 2016, but it would be in the year 2016. I think we'll stop here for part 1. In part 2, we'll take a look at an example where we have a continuous decay rate. I hope you found this helpful.